I welcome you in this course on control systems. It is basically a 4 credit course. So 3 theory classes, 1 tutorial, and so far as practicals are concerned, there's a separate lab associated with this subject. We have a separate lab that's been taken by electrical engineering department. The books recommended are for this course are, first would be Control Systems Control Systems Engineering. The author is Norman S. Nice, and the publisher is John Wiley and Sons. The second book is Control Systems Principles and Design, and the author is M. Gopal. This book, so far is concerned, the publisher is Tata McGraw and Hill Limited. We'll mostly be using these 2 books, Control Systems Engineering by Norman S. Nice, and the second, Control System Principles and Design by M. Gopal. There are basically 5 units in this course, and the first unit is Introduction to Control Systems. Now, before coming to the definition of control system, we'll first discuss some examples of control systems. Examples of control systems. Say, for example, after doing a physical work or an exercise, when we do some physical work or a strenuous exercise, the temperature of the body rises. And in response to this, what happens is that the body produces sweat. And this sweat on evaporation. This sweat on evaporation produces cooling. So this is a natural control system. After doing an exercise, the temperature rises, and in response to it, what happens is that the body produces sweat, which on evaporation results in cooling, and hence the body temperature is controlled or regulated. Or we can say that the temperature is maintained at some temperature. So this is our example 1. Another example can be, for example, after eating food, what happens is that the food after eating gets converted into glucose or sugars. So when this food gets converted into glucose, the sugar level in blood increases. Which is not good for health. So in response to this increased sugar level, what happens is that pancreas secretes insulin this insulin regulates the blood, regulates the sugar level, the sugar level in the blood. So this is a naturally occurring control system. What happens in case of diabetic people? So the patient is having diabetes. The problem with diabetic patients is that when they eat something, it gets converted into sugars, and this raises the level of sugar in the blood. And on contrary to a normal person, what happens in case of diabetic people is that pancreas doesn't secrete sufficient amount of insulin so as to regulate the level of sugar in the blood. That's why they have raised sugar level. Another common example can be, for example, if we have to cross a road, say for example we have a road and there are vehicles plying on this road. Let's assume this is a vehicle, it's moving in this direction, and you are somewhere here and you want to cross this road. You are at point A, for example, and you want to cross this road, and the vehicle is at point B. Now what happens is that you first look towards the vehicle, and intuitively you try to find whether you can cross the road before it hits you. So there is basically a sensory mechanism. There is basically a sensory mechanism by which you come to know whether you can cross the road or not. This sensory mechanism, this includes your eyes, ears, brain, etc. So the eyes, they look at the vehicle, the ears also try to hear to the sound produced by the vehicle, and it is finally the brain that takes the call whether you can cross the road or not. So this is all in all a control system which intuitively works and lets you know whether you can cross the road without being hit by the vehicle. So now coming to the definition of a control system. Now let's define a control system. So a control system basically consists of subsystems. Or processes, or sometimes also called as plants, assembled for the purpose of controlling the output of the process. So any control system will takes an input, processes the input, in a predefined manner, and generates a desired output. Some more examples from day-to-day life are, for example, let us take few examples. A refrigerator, an automatic iron, an electric geyser, for example, Now, so far as a refrigerator is concerned, for example, we set the temperature to some value. When we set the temperature to some value, what happens is that the refrigerator maintains that temperature. Likewise, an automatic iron so far is concerned. An automatic iron is again an example of a control system. What happens in case of an automatic iron is that we set the temperature to some value. When we set the temperature to some value, what happens is that when the temperature reaches to that value, the automatic iron automatically turns off. So while ironing, what happens usually is that we first set the temperature to some value and then go on ironing, and when we iron the clothes, the temperature doesn't reach to a higher value which otherwise would burn our clothes. So likewise, an electric geyser, for example, we set the temperature of the electric geyser and it maintains the temperature of the water within the geyser to that value only. The temperature doesn't go beyond that value. When the temperature goes beyond that value, tries to go beyond that value, rather when the temperature reaches that value, the geyser automatically turns off. So these are all examples of control systems. So in case of refrigerator, for example, the refrigerator is a control system. In case of an automatic iron, it works like a control system. Now, for example, in case of an air conditioner, which is also an example of air conditioner, is again an example of a control system. What happens is that the air conditioner maintains the temperature of the room at some fixed value. Here, air conditioner is a control system and the maintained temperature is the desired output, for example. Likewise, the desired output in case of a refrigerator is the temperature that it maintains. Again, in case of a geyser, the desired output is the temperature that the geyser maintains of the water which is within the geyser. So now we can draw the block diagram of a control system. Block diagram. So we have this as a control system. We have an input to this. We have an input. And we have an output. The input is also sometimes called as stimulus. And the output is also called as response. This input may also be sometimes written as desired response. And the output can be named as actual response. We'll discuss it in a short while. So we have something called as desired response, which is also called as input, and we have something, the actual response, which is the output. Say for example, in case of an electric iron, we want to maintain its temperature at 70 degrees Celsius, and the actual temperature is, say for example, 67 degrees. So the desired basically is 70 degrees centigrade, but the actual that the control system is producing or delivering is 67 degrees. So this is sometimes called as desired is the response that we intend to have, but in actual we are not having the exact value. The actual value of the response can be 67 degrees. So desired response in general, desired response in general may not be equal to the actual response. The difference between the desired and the actual response is called as the error of the control system. Error of the control system. It is the difference between the desired and the actual response. Desired response minus actual response. Now let's try to understand these things like the input or the stimulus, output or the response, or the actual response and the desired response. We'll try to understand these things by the following example. Suppose we are inside a tall building, a multi-story building. Let's assume this is the ground floor, G for ground floor. Then we have the first floor. This example is from the first book, Norman S. Nice. So this is the first floor, this is the second floor, say for example, third floor, fourth floor, and fifth floor, and then the sixth floor, for example. So we have a multi-story building having multi-stories, having multiple stories. So say for example, we intend to move from ground floor to the fifth floor. We have this as the lift or an elevator. Let's assume this is the lift or the elevator. So we intend to move from ground floor to the fifth floor, which is this. So the first thing we do is that we'll push the button 5, which is on the door of the elevator. After pushing this button, the lift will start moving up, and eventually it reaches the fifth floor. The elevator will reach the fifth floor. Say it reaches eventually here. The fifth floor. So this is where we are. From ground floor, it reaches the fifth floor after we push the button 5. So the push to the elevator is the input. When we push the button, the push to the elevator is the input, which is basically a step function, a constant value. If I represent it graphically, this can be shown as, I have time axis along x-axis. This is our time axis, and let us assume the y-axis so far is concerned. The y-axis is the position of the elevator. So this is the first floor, this is the second floor, this is the third floor, fourth floor, fifth floor, sixth floor. Now when we press the button 5, we say this push is the input basically. So this is what happens. This is the input, which is a constant value 5. As I said, the input is also the desired. This is also the desired output. Desired output as we want to reach the fifth floor. So as can be seen from this plot or from this example, the push is basically the input, and this is also the desired output as we intend to reach the fifth floor. So this is a constant function and has a constant value for all time t. It has a constant value of 5. We are pushing the button at t equal to 0. This is our t equal to 0 point, and we push the button at t equal to 0. Now when we push the button, the elevator starts moving up. It starts moving up, and eventually it comes closer to the fifth floor, and then the lift stays there for a longer duration. So this this curve basically is the response of the lift, is the response of the elevator. So it takes some time. From t equal to 0, it goes up, and eventually it reaches this constant value. So this part of this curve is called as this part of the curve when the lift is moving up from the ground floor to the 5th floor. This part is called as the transient response. This is the transient response. And this part of the response, let me use a different color. And this part of the response, let me encircle it. This part of the response is the steady state response, as there is no change after this steady state response. Now, as can be seen, this curve in the steady state response, there is a difference. Let me use a different color, yellow color. So this difference between the two curves, this is basically the error of the control system. Our aim basically is that it should reach the 5th floor exactly, but it stays slightly below the 5th floor. As can be seen here, our aim is that lift should be exactly here on the 5th floor, but it is slightly below the 5th floor. So this part is the error. This part basically is the error, which is also called as the steady state error. Steady state error. Now, as can be seen from the plot, let me redraw it. So this basically is the input, which is a constant value of 5. But when it comes to the output, what happens is that it stays just below the value of 5. So there is a difference. This difference, as I said, is basically the steady state error. This difference between the actual, the desired response, and this part of this curve is basically the actual response. This is the actual response or the steady state value, actual response. So the difference between them is the steady state error. Is the steady state error. This value is the steady state error. The difference between these two curves, this difference is the steady state error. So it is obvious from this curve that when we press the button at t equal to 0, the input is 5. But in response to this input, the elevator takes some time to reach to the 5th floor. The elevator cannot instantaneously jump from the ground floor to the 5th floor, as it takes some time, as can be seen here from this time axis, that it takes some time to reach to the 5th floor, as it has to cross the 1st, 2nd, 3rd and the 4th floors, and eventually it reaches the 5th floor. This is basically common with all control systems. Whenever we apply an input command to the control system, the output is always gradually reaches the steady state. So the input can be instantaneous, as for example in this case, but the output is always gradual in nature, as it takes the control system some time to do the processing so as to achieve the desired output. So the transient region, let me again draw this curve. So this part of the curve so far is concerned is the transient response. That is, it takes some time to reach the final state. And then we have another region, which is the steady state region. This part of the curve is the steady state response. Steady state response. The actual input, as I said, is this constant value. In this case is the constant value 5, and this difference as I have been saying repeatedly, is the steady state error. This difference is the steady state error. In the steady state region, we can say that the final output has been generated. This is the final output. And by that we mean that the control system has now stopped working. When it has reached the final value or the final steady state, we say the control system has stopped functioning. While in the transient period, the control system continuously works so as to achieve the desired output. Now coming to the accuracy of the control system, the last thing that we'll discuss before priors is the accuracy of the control system. It is time for Isha prayers here. The time here is 7:57. By 8:10 the Isha prayer will start. So I'll try to wrap it up within these few minutes. So all in all, so far as the accuracy is concerned, now the difference between the actual response and the desired response of a control system is the error of the control system. This is what I said. So if this error, if this value here, if the two curves coincide, have a very small difference. In other words, the steady state value is the same as the desired value, or the actual response is the same as the desired response, then we say the error is minimum and the control system that way is more accurate. So in a nutshell, as I can say, the error of the, as I said, error is the difference between these two values, the actual and the desired. This is the steady state error, sometimes also called as steady state error. And the steady state error, the value of the steady state error should be within some specific limits which are being specified by the system engineer. This will do for the day. This was our first lecture. In our next lecture, we'll discuss system configurations. For example, we'll discuss open loop control system and closed loop control systems. Till then, Khuda Hafiz.